From space, we don't see the borders that divide us, the arbitrary lines in the sand that have kept humans at war somewhere throughout our history. But it is a sad constant. What has changed dramatically is the technology of war, which inevitably led us down the road to nuclear weapons, the most devastating instruments of war ever devised by human beings. Ironically, nuclear weapons have served as an unequaled deterrent to war. The specter of the mushroom cloud has focused world leaders on finding other ways to resolve conflict. It's an outcome that would likely surprise even the brilliant minds who gathered here in the mountains of New Mexico during the dark days of World War II, determined to harness science to end the fighting.
Hello, I'm Miles O'Brien. Welcome to Los Alamos. As you know, this is the birthplace of the atomic bomb. Over the years, the weapons devised here have literally changed the course of human history. And in fact, now it is no longer pie-in-the-sky thinking to imagine a world without nuclear weapons. So what does that mean at a place like Los Alamos? It's not what you think.
To be clear, the laboratory does not make nuclear weapons policy for the nation. It provides the technical solutions to make the policies possible. There are a lot of smart, busy people doing amazing, cutting-edge research here, including 3D computer modeling that took me inside the fundamental forces that power our sun, our universe for that matter. So the mission here is the same as it ever was, to provide the nation with a safe, secure, and effective nuclear deterrent using the best science, technology, and engineering available.
For 65 years, we have been designing and maintaining nuclear weapons, not for the purpose of using the nuclear weapons, but for the purpose of deterring their use. And that has been successful. As we move on to the future, we're going to have that same challenge of maintaining a nuclear scientific capability, again, to deter the use of nuclear weapons.
We still have the mission of providing the deterrent for the country. You know, somebody at the end of the day has to be able to say to the President and to the Congress, you can count on these systems.
Today at Los Alamos, the work has changed significantly from the early days. They're not designing or building new weapons here anymore, nor are they testing bombs beneath the Nevada desert. That ended in 1992. It seems as if the arms race is winding down.
So today, I state clearly and with conviction America's commitment to seek the peace and security of a world without nuclear weapons. I'm not naive. This goal will not be reached quickly. Make no mistake, as long as these weapons exist, the United States will maintain a safe, secure, and effective arsenal to deter any adversary.
The laboratory's role in developing and maintaining that arsenal began in 1939, when Albert Einstein penned a letter to President Franklin Roosevelt, warning him it may become possible to set up a nuclear chain reaction in a large mass of uranium, by which vast amounts of power and large quantities of new radium-like elements would be generated. The letter from Einstein prompted FDR to create what became known as the Manhattan Project. The heart and soul of that huge, far-flung operation was this place, the Los Alamos National Laboratory. This is one of the few buildings of that era that still remains. It's a very significant one. It's known as the V site. The leading physicists of the world came here to try to solve the problem of the nuclear weapon. And it's in that building that they assembled the first test article, something they called the gadget. On July 16, 1945, they tested the gadget in remote southern New Mexico. It worked. Within weeks, the U.S. would drop atomic bombs Little Boy and Fat Man on Hiroshima and Nagasaki. A long, bloody global war was over, and a new kind of war began. In 1949, the Soviet Union detonated its first atomic weapons, and a terrifying race for nuclear supremacy was on. At their highest points during the Cold War, the two superpowers combined had more than 70,000 atomic weapons aimed at each other.
Отсчет эпохи ядерного разоружения. The exchange a few minutes ago of the instruments of ratification means that the era of nuclear disarmament has begun.
We must not stop here, Mr. General Secretary. There is much more to be done.
Some key treaties came out of historic summit meetings, and the number of nuclear weapons started to decline. Since the height of the Cold War, the U.S. has reduced its stockpile of nuclear weapons by more than 90%. Today, the United States has the smallest nuclear weapons stockpile since the Eisenhower presidency.
When I look back at the Cold War, it's, to me, very clear that the presence of nuclear weapons brought a sense of caution into international decision-making that hadn't been there prior to the Second World War. And while nuclear weapons have not stopped warfare, we have not seen warfare on a global scale since the Second World War. I believe that's a good thing for the world. It's something I've been willing to commit my career to.
And you think the work that has been done here since the Manhattan Project has made that a reality?
Absolutely. Absolutely.
Now, here in the cradle of the atomic bomb, they are grappling with the issues of age. Because nuclear weapons operate in unprecedented conditions, extreme temperatures and pressures, and blindingly fast speeds, how best to ensure the weapons, as they get older, are safe and will work if needed, or not if their security is ever compromised? For one thing, world-class supercomputing.
The advanced computing capability plays a role in helping scientists simulate and understand designs of nuclear devices, and allows us to be able to certify nuclear weapons without actually testing it at the Nevada test site.
Los Alamos computer scientists have developed three-dimensional, full-motion computer models that predict the behavior of weapon materials and components, and ultimately the overall performance of a nuclear weapon. These simulations combine data gleaned from nuclear tests and from hundreds of individual experiments on everything from the most basic materials, like metals, plastics, and foams, to the most complex weapon components, such as plutonium and high explosives.
All right, so Kim, what are we looking at here, first of all?
So we're seeing a visualization of a shock tube experiment where we have...
Physicist Kim Scott took me inside a shock wave, where materials of various densities traveling at high speed slam into each other.
And so what kind of insights can you get by looking at this?
So it's really difficult when you have a complicated experiment like this and you're trying to model it on a computer, and there are lots of 3D effects that are going on to visualize it in your head when you're just seeing numbers scroll across a computer screen, right? And even just taking a 2D slice through a complicated simulation of an experiment doesn't give you the full picture. So being able to step inside of it brings out details that you wouldn't have imagined and makes you think about physics behind what you're doing that wouldn't have occurred to you maybe necessarily before.
Nathaniel Morgan is part of the team that helps make the 3D visualizations by constantly improving the computer models used with experimental data that replicate the real world in cyberspace. To do that accurately, they employ some of the fastest supercomputers in the world.
Nuclear weapons are very nonlinear. They have very complex areas of physics. They operate from room temperature to temperatures at the core of the sun. So there's a wide range of physics, a wide range of areas of difficulty, and it is a very challenging problem and requires a tremendous amount of computing power to solve the equations describing those regimes.
To make sure the lab scientists and engineers are getting the right answer, they do a lot of non-nuclear testing. It can give them a glimpse of what happens to the components of weapons as they age and are modified over time. The new data is used to update the computer model.
So what goes on in here now?
So this is where we do our dynamic experiments.
Dynamic indeed. Frank Merrill showed me the Los Alamos Neutron Science Center, or LANCE. It takes pictures using protons. They are accelerated by magnets over half a mile in this pipe, then focused on a conventional explosion that happens much, much faster than a blink of an eye.
We managed to take pictures at rates of about a millionth of a second and look inside of these systems and understand what's going on.
And what do you learn when you do that?
So we learn how high explosives detonate and the properties of high explosives as they detonate, how metals, when they're in contact with detonating high explosives, how they break up, how they fail, and the consequences of that failure.
Merrill showed me one of those movies. 19 frames captured in a few millionths of a second. It boggles the mind.
This bright area here, that's the high explosives that didn't actually detonate but was just compressed by this high pressure front that wrapped around it. And you can see that it isn't as well predicted in this model as big as we measured.
So in this case, that experiment would probably change the model.
That's right. So this experiment forced our model community, and this was about 5 years ago, to go back and refine their models of how these transitions happen.
So right there in a nutshell is why you still need to do these tests.
That's right. So there is still physics that isn't completely understood in how these systems work.
The model is not done.
No.
The model is further refined at the Dual-Axis Radiographic Hydrodynamic Test, or DART facility. Here, they create a non-nuclear mock-up of a nuclear device. 2 powerful accelerators generate X-rays that capture images as the simulated plutonium pit implodes.
We use large 6-foot diameter, 2.5-inch thick steel vessels to contain the explosive experiment. And what does that really do for us? Well, first of all, it prevents the hazardous materials from contaminating the environment. Second, it actually prevents the firing point itself from being contaminated. We take the electrons, we accelerate them to very high energy. They reach a velocity that's close to the speed of light, and then we slam them into a target to generate high energy X-rays. The high energy X-rays that we generate then, just like a dental X-ray, propagate through a mock nuclear device, allowing us to take pictures of that mock nuclear device. With one of the axes, we take a single picture, basically stop the motion of materials. With the other axis, we take 4 pictures, so we actually can see how the materials move as a function of time. And in fact, gives us much more information to be able to compare with our simulations and certify the stockpile in the absence of testing. DART is a one-of-a-kind facility. There is no place else in the world currently where we have 2 axes to take X-ray images of mock nuclear devices.
Reliance on non-nuclear testing and computer modeling increases the degree of difficulty for the scientists, engineers, and technicians charged with managing and assessing the aging stockpile. Denise Korzekwa is in charge of making many of the components used in experiments.
Because we have to find ways of being able to test these materials without underground testing. We have to make much smaller scale test items. We need to look at clever ways of doing things because our restrictions on what we can do are different now than they used to be. So what we do now is we do a lot of testing on the aging of materials. So we look at how they're reacting over time. We also do some development on how to make things that we want to make in case we need to replace weapons, like in plutonium. If we need to replace a pit in plutonium, we are looking at ways to make it.
So what are these pits we've been talking about? Modern nuclear weapons have 2 main components, the primary and the secondary, both held within a metal containment shell. The primary's central core, called a pit, is like a ball of plutonium surrounded by high explosives. When the high explosives are detonated, the force of the explosion, directed inward, compresses the nuclear material inside the pit into a smaller and smaller volume. This implosion generates a fission chain reaction, and a rapid burst of nuclear energy surrounds the secondary. The heat and pressure generate fusion and fission reactions in the secondary, creating tremendous amounts of nuclear energy and ultimately a thermonuclear explosion. Here at Los Alamos, they're not only working hard to understand what happens to weapon systems as they age, they're also focused on keeping an experienced workforce intact, even though there are fewer opportunities for them to hone their unique craft. All of this work and expertise is funneling into a brand new building here at Los Alamos, the first nuclear research facility built in the U.S. in 30 years, specifically designed for increased safety, security, and for better safeguarding the environment. Ken Lanes gave me a tour while it was still a construction site.
Why is it important to have labs like this?
We still have to take care of the stockpile that we have. We have to be agile in case there's ever an event. Other countries are not following the same route that we are in terms of reducing our stockpile. There's still a lot of interest in nuclear materials, not only for weapons purposes, but also for medical isotope research and for nuclear power.
The lab plays a vital role helping stop rogue states or terrorist organizations from developing their own capability to build nuclear weapons.
It takes a weapons laboratory to understand a weapons laboratory. So as other nations may decide to become proliferant in their viewpoint, it takes the expertise and the facilities here to understand what it is they're actually doing.
Imagine that you have a world without any nuclear weapons. Who are the people that are best able to help make sure that it remains that way? I'd claim it's the people who work in this program.
However close we get to zero, and even if we would actually approach zero nuclear weapons at some time, everyone in the world knows that the scientific capability of the scientists in the laboratories is still there. And that in itself is a powerful deterrent.
So is a place like Los Alamos relevant in a world that seeks to eliminate all nuclear weapons? The answer is not as simple as it seems. As it turns out, the imagination, the creativity, the agility of the people who work here are just as much a part of our national security as the weapons themselves. Thanks for watching.